Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Chemical Reaction Engineering Part 3, Analysis of Plug Flow Reactor with Multiple Reactions. Plug flow reactors are the most commonly used type of reactor in industrial chemical processes. Shown here is a homogeneous PF4 involving single reaction. Reactants A and B react to form C and D. A is partially converted and B is completely converted. So the reactor outlet contains A, C and D. The products of the reactions are C and D. No other reactions are taking place. So depending on the conversion of A, the product amounts are determined. Multiple reactions. In multiple reactions, the main product of interest is selectivity of the desired product. In many industrial processes, the chemical reactions occur at a given set of operating conditions in multiple pathways. The operating conditions are selected to optimize the reaction rate for the desired reaction pathway, which is the main reaction pathway. However, several competing reactions occur both in parallel and series, leading to production of undesired products. These side reactions divert costly raw material, that is reactants, and results in lower yield of the desired product. Illustrated in this figure is a plug flow reactor where 4 reactions are occurring. The feed consists of reactants A and B, and the 4 reactions are A plus B forming C and D, A combining with B forming E and D, A combining with B forming F, and product C combining with the reactant B forming products G and D. So the reactor outlet stream consists of A, C, D, E and G. Reactant B is consumed completely. C is a desired product in this reaction. What do you observe from the above reactions? Though C is the main product you want to produce, reactions to form EFG are competing for the same reactants A and B. What factor will determine that the reactor outlet will have maximum concentration of product C and low concentration of byproducts? It is a reaction rate constant K for the individual reactions. The rate constant will influence the rate at which the desired reaction pathway should proceed so that it will lead to maximum consumption and conversion of reactants to the desired product. In the four reaction pathways, the individual reaction rate constants are denoted as K1, K2, K3 and K4. The rate equation for any reactant is sum of the individual reaction rates for all the reaction involving that reactant. The rate of consumption of A and B are RA equals minus K1 into Ca into Cb minus K2 CaCb minus K3 CaCb. Rb equals minus K1 CaCb minus K2 CaCb minus K3 CaCb minus K4 CaCb. The negative sign indicates consumption or disappearance of A and B. Rate of formation of C, E, F and G are Rc equals K1 CaCb minus K4 CcCb. Re equals K2 CaCb. Re equals K3 CaCb. Rg equals K4 CcCb. From the individual rate of reaction, the relative rates are determined as shown here. If you have to maximize the reaction rate for formation of product C, which is the desired product, the relative ratio has to be greater. Manyfold it has to be increased for this reaction. Two ways to control the reactions for favorable product distribution are increase of reaction rate for desired reaction compared to side reactions, study the activation energy of the reaction and fix the reaction temperature. If the reaction pathway 1 is the desired one, then the ratios of K1 to K2, K1 to K3, K1 to K4 should be adjusted in favor of K1. The activation energy of the competing reactions should be studied. If E1, the activation energy of E1 is greater than E2, the reaction temperature should be maximized. If the activation energy E1 is less than E2, the reaction temperature should be kept low. Let us see an example now to strengthen your understanding on how multiple reactions are managed for optimum reactor performance. Problem description: allyl chloride, which is also called 1-chloro-2-propene, is produced by thermal chlorination of propylene at 500 degrees centigrade and 0.5 bar pressure. 20 kg moles of chlorine and 100 kg moles of propylene are fed into the reactor. Chlorine is the limiting component. Allyl chloride forms by substitution reaction between propylene and chlorine. It is represented by equation 1 below. This figure illustrates the allyl chloride plug flow reactor with feed streams and product streams. In parallel to the main reaction, side reaction also occurs at the operating conditions, which is an addition reaction between propylene and chlorine to form dichloropropane. The above mentioned reactions taking place in the reactor are shown here. Propylene plus chlorine forming allyl chloride in the first reaction, propylene and chlorine formed by addition chlorination to form dichloropropane in the second reaction. Allyl chloride yield in the reactor is 85%. Chlorine conversion is 100%. Determine the product distribution and selectivity of this reactor. Now the solution part. Problem data available for solutions are chlorine at reactor inlet 20 kg moles, propylene at reactor inlet 100 kg moles. Given that chlorine conversion is 100%, the chlorine reactor outlet concentration is 0. So chlorine reacted is 20 moles. Yield of allyl chloride based on chlorine is 85%. That's the value given. Allyl chloride is produced by the reaction 1. If there is no side reaction, the entire amount of chlorine will be converted into allyl chloride. So the maximum allyl chloride would be produced if there is no side reaction is 20 kg moles. Actual yield of allyl chloride given is 85%. So the allyl chloride produced is 70 moles. Chlorine consumed for allyl chloride is 17 moles. That means the remaining chlorine would be consumed for dichloropropane. So the chlorine consumed for dichloropropane is 3 moles. Next, let us make the propylene mole balance for the reactions. Initial number of moles, that is propylene in the reactor inlet, is 100 moles. It's an equimolar reaction. In the first one, the propylene reacted for reaction 1 is 17 kg moles. Likewise, propylene reacted for reaction 2 is 3 moles, 1 mole for 1 mole of dichloropropane. So the balanced propylene in the reactor outlet is 100 minus 17 minus 3 is 80 kg moles. Every mole of propylene and chlorine reacted, you will produce 1 mole of hydrogen chloride also. So 17 moles of hydrogen chloride will also be produced in the reaction 1. Now we can write inlet and outlet product distribution. Propylene feed 100 moles, product 80 moles. Chlorine it's 100% reaction and conversion. So feed 20 moles, product is 0 moles. Allyl chloride, feed 0, product 17 moles. Dichloropropane, feed 0, product 3 moles. Hydrogen chloride, feed 0, product 17 moles. So the total number of moles in the feed is 120, the product is 117. The total moles will not match in this case between the product and the feed, because if you look at the reaction 2, 1 mole of chlorine and 1 mole of propylene react to form 1 mole of dichloropropane, which means 2 moles give you only 1 mole. So there is a reduction in number of moles. So in terms of mole balance, the feed and the product will not match. But if you look at the mass balance, it will match. Selectivity of the desired product, allyl chloride, based on products can now be calculated. Selectivity equals allyl chloride produced to total products produced, which means 17 into 100 divided by 20 equals 85%. In the example shown above, there are other series and parallel reactions are occurring, but at a smaller level, so that they are ignored to make the illustration simple for understanding. As we become more confident in the analysis, you can analyze all such relevant reactions, however small, and determine their influence on the overall reactor performance. In industries, every possible reaction is analyzed and included in the material balance. The key to maximize the desired product formation is to determine the optimum operating conditions. In most examples, temperature has a significant impact on the reaction rate. Some undesired side reactions are more favorable at certain temperatures compared to the desired reaction. So fix a temperature at which the desired product rate is maximum and the rate for the undesired reaction rate is minimum. Now let me ask you a question. Apply the knowledge gained earlier in this discussion to answer. Out of the two reactions, what made the reactants to choose the reaction pathway 1 and produce ALC as a greater proportion of the product? At the reaction temperature of 500 degrees centigrade, rate constant for allyl chloride KALC is 0.788. The rate constant at the same temperature for dichloropropane KDCPA is 0.022 in the unit shown. So the rate constant for reaction 1 is manyfold higher than for reaction 2 at 500 degrees centigrade. At a much lower temperature of 300 degrees centigrade, the side reactions dominate as their rates are appreciably higher compared to the desired reaction. This is an advantage which is made use of in optimizing the reactor performance. Another important parameter considered usually in the optimization of the reactor performance is activation energy. Activation energy of allyl chloride is 27,200 BTU per lb mole. Activation energy of dichloropropane is 6,860 BTU per lb mole. Hence, rising the temperature of the reaction will favor allyl chloride formation. That is the reason why high temperature of 500 degree is selected. Mixing of reactants at the reactor inlet with special mixing devices is another engineering aspect to maximize the desired product formation. To avoid series reaction of product getting converted to undesired product, the concentration of the limiting reactant is reduced considerably within a very short distance in the reactor so that it is not available for further reaction with propylene. So the strategy normally followed in multiple reaction is to select appropriate reaction pathways, optimize operation condition, better heat distribution, which ultimately lead to higher selectivity of desired product. Reaction is the most critical step in determining the production cost. Suppression of undesirable side reactions and consecutive reactions of the desired main product will result in increased raw material consumption, hence high operating cost. So the focus of reactor design is to minimize byproducts, which will ultimately lead to maximization of the yield. Lower byproduct formation means lower operating cost. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Hope this presentation with narration and animation was useful. Please give your comments, if any, about this course after you finished viewing the video. Share with your friends and colleagues to reach out to large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing the knowledge base. Thank you for watching.